With the concept of phasor, we can transform ODE into algebraic function with complex coefficients, and then transfer the steady-state analysis of the dynamic circuits with sinusoidal excitation into the resistive circuit analysis with complex coefficients. Then all the methods we introduced in part 1 of the course are adaptable. It's amazing. We will go through the fascinating journal with 7 examples. Firstly, let's have a look at the initial value problem for dynamic circuits with sinusoidal excitations. Please see, at first, the switch is closed. The sinusoidal excitation powers the inductor. The switch is open at t equals 0, which changes the topology into that the sinusoidal excitation powers the resistor and the inductor. We need to find IL, UR equals UL, and UR at t equals 0. We need to find IL plus. We need to know that steady state of L in order to find IL plus. Then we need to draw the steady state circuit before switching. It's like this. The circuit is very simple. We can find that IL equals this. So the time domain expression for IL is like this. With the time domain expression before switching, we can find IL0 minus. Next, according to the switching law, we know this value is IL0 plus. In order to find UL0 plus and UR0 plus, we need to draw the 0 plus equivalent resistive circuit, in which the voltage source should be the US t equals 0, like this. Now the inductor is substitute for the current source, whose value is 0 plus value. For this simple resistive circuit, we know this. Next, in order to find UL, we need to utilize KVL through this path. Then we finish the solution process. You can find that even though we are asked to find 0 plus values, we need to find 0 minus value for inductors. And in order to find the 0 minus value for the inductor, we need to solve the steady-state circuit before switching. That is, we need to solve the SSS circuit before switching. So we combine the SSS and time domain analysis for dynamic circuits together. The second example is also the combination of the time domain analysis with SSS. Let's see. The excitation is sinusoidal. The switch is closed when t equals 0. We know it's a 0 state and are supposed to find IT. We introduced the 3 elements method in lecture 50. Any branch variable of the first order circuit can have such an expression. Here, the I steady t means the time domain expression of the branch variable. I steady 0 means the value of the steady state when t equals 0 plus. For RC tau equals RC, for LR it's L over R. We know that the circuit is 0 state, so I0 equals 0. And the circuit is a simple RL circuit, so tau equals L over R. Then the key for solving the problem is a steady-state time domain expression. For such a circuit, after the switch is closed, it means that the voltage powers the resistor and the inductor, so we can draw the circuit under phasor domain. For such a resistive circuit with complex coefficient, It's easy to find out this. We can transfer the denominator into the modular and the phase form like this. So the equation is this. With the solution of phasor, we can easily write its time domain expression. So we know its 0 plus value is this. By substituting these two solutions into this expression, we can find the time domain expression of IT and then finish the analyzing process. For such a standard zero-state circuit, we need phasor method to find the steady-state values. Here, I'd like to leave a question. We only provide the general expression of the source initial angle. We want to ask which value of phi u will result in no transient process for current I, and which value of phi u will result in the maximum value in the transient process.